So just wanted to let you know that we had to make a little bit of adjustment because this event is being streamed live, and to our external stakeholders, sponsors and partners, specifically to the National Academy of Inventors community. So welcome back, and I am very, very grateful to our students, our board members for yesterday's sessions and today's sessions. The students have been doing a great job in presenting their research and innovation projects briefing. I wanted to give you a little bit of background for this particular event. And to start with, my name is Atam Dhawan. I'm the Senior Vice Provost for Research and also the President of the National Academy of Inventor chapter at NJIT. I'm also the Executive Director of the Undergraduate Research and Innovation Program and also the Executive Director for the Center for Translational Research, that is NSF funded through the Accelerating Research Translation Program of the Technology, Innovation and Partnership Directorate. It's my great pleasure to welcome you all, and specifically I am very grateful to the National Academy of Inventors for their tremendous support and the leadership in this particular nation. Before a few years ago, we only had the three national academies, the National Academy of Science, Engineering, and the third one is Medicine. But it is really important for the societal impact as well as the economic impact that we recognize and promote the innovation and its translation towards inventorship and promoting the pathways for entrepreneurship and commercialization. And that's exactly what NAI mission has been and is there. I'm very grateful to the leadership of the National Academy of Inventors, specifically with Dr. Paul Sandberg. He's the president, and under his presidency and the vision, and also a very, very tremendous synergy with National Science Foundation, Dr. Panchanathan, who was one of the founding board of directors of the National Academy of Inventors, and many other visionary people who brought this strategic initiative and very visionary initiative into the limelight to promote innovation and inventorship not only across the nation but across the globe. This is particularly important to support and to be a part of the National Academy of Inventors, and for which I'm not only grateful, but I'm very proud that NJIT is a well-known member and chapter for the National Academy of Inventors, through which we have done several activities. We do 4 or 5 NAI-NJIT workshops on emerging topics, and also we follow through the Student Inventor and Innovator Club, for which you are competing today. So just for our audience, I wanted to give a very quick overview of the event that we started yesterday and is continued today. So can we put my slide, please? So yesterday we started the Undergraduate Research and Innovation Program Summer Symposium at NJIT. This particular program, as you heard in the morning, it started actually 2012 with about 12 students in a classroom that we used to call Interdisciplinary Design Studio, to look into the students' ideas of creating innovative solution to the unmet market and societal needs for high impact, not only from the technological solutions, but also towards commercialization and looking into the feasibility of making an economic impact. So far, actually, this slide does not include this investment. So it is about more than $6 million that we have invested into this particular program to support a student through the student's stipend, NSF REU, Honors College, Summer Research Institutes, NSF I-Corps Hub, and several other programs evolved leveraging the original interdisciplinary design studio, which then later turned into the university-wide initiative of undergraduate research and innovation, which is now supported by both NAI-NJIT chapter as well as the Center for Translational Research. So thanks to the sponsors and as well as the board members, and our board members, many of them are also the member of the NAI-NJIT chapter and the fellow of the National Academy of Inventor. Now, yesterday we had about 112 presentations, excellent presentations from the student, and the board members agreed with me when I mentioned that many of these presentations, when I hear them and they heard them, we just couldn't believe that these are undergraduate students. They look like PhD students or very polished inventors who are making a pitch to the investor board. So this is the platform for the students, our young innovators and inventors, to present and make a pitch of their innovative ideas, their preliminary results on the work that they have conducted during this particular summer, in order to develop a skill set that tomorrow they are going to be using as the leaders of our society and the front of the innovators and inventors. So we are very proud to provide this opportunity to our students through our partners, through our board members, through our sponsors, through the National Academy of Inventors, that they are learning these leadership skills, and we look forward for their contributions in continued evolution of the technologies and making the world as a better place. And what President Lim pointed out this morning, the joy of invention and improving the quality of the life, sustainability, healthcare, and dependency on the data revolution, but making it secured and making it trustworthy. When we come to that particular part and looking into that, the enabling technologies, as I see today, the revolutionary enabling technology, if we look into from a very broad spectrum, we will find something like material science and engineering, which is a common enabler, because something that you put the devices, it starts from the material. And in that particular category, you call today's and tomorrow's future depends on this particular very, very innovative approach, which is called quantum. So we have done a lot with the silicon in terms of the chips and everything, but now it is the time that the Moore's law does not continue to hold in that particular evolutionary space. So we need to find another dimension in another space which the quantum materials have the potential to fill that particular gap for the next level of the technologies. But at the same time, as NJIT has put together the 5 research cluster, these clusters belong to the current trend of the technologies development for meeting the societal need, and also for the tomorrow's trends and the vision of the technologies that you and I and everybody else imagine that it should happen in the future. These clusters are bioscience and bioengineering, specifically related to the healthcare innovations and the foundation of those technologies which are going to help the society become healthier and sustain that health in the society. The other one is environment and sustainability. The other research cluster is material science and engineering. And then the two other clusters are robotic and machine intelligence and data science and management. We talked this morning a little bit about that everything that we do today, when the technology or the related protocols reach to the users in the applications that the society needs, or we implement those particular innovative solutions in the real world, we see that a lot of things revolve around generating the data from the use of the technology and doing the data analytics to see whether it is serving its purpose. That is the sort of minimum requirement. But when you develop the technology, you need to come across many kind of modeling and simulations and the other type of optimization type of methods. And we have been using computers for that. But now there is a new frontier, which is the data analytics driven by the AI, advanced machine learning, generative AI, and also the digital twins. So today, we are very, very fortunate and very grateful that one of the world-renowned experts is with us to talk a little bit about the generative AI and digital twins. And he has been doing that for decades in the leadership position at Siemens. Dr. Amit Chakravarty is a principal scientist with Siemens Technology. He has been with Siemens since 1996, and since 2003, he has been leading a research group, first as the program manager, and then since 2012 as a research group head. His major contribution and expertise are in the emerging area of hybrid digital twin that works in the interface of simulation, AI, machine learning, and control with optimization and risk modeling. All of those things which are very, very critical to develop a technology and translating it for the user-inspired applications. Among many contributory areas, Dr. Chakravarty has led the groups and the technology development portfolio in the areas like gas turbines with conveyor belts for automotive manufacturing, energy optimization and high performance buildings, power flow optimization for electric grids, and semantic modeling of the customer and manufacturing data. All of these have a direct impact to the society for its well-being, but also for its economic development and the job growth. For his contribution and many, many innovative ideas, Dr. Chakravarty won Siemens Lifetime Achievement Inventor of the Year Award. He doesn't look that old, so getting at the younger age this Lifetime Achievement Inventor of the Year award he received in 2021 speaks for his quest for invention and innovation itself. He also receives the Edison Award in 2022 and again in 2024. So it's my great honor and pleasure to ask you to join me in welcoming Dr. Amit Chakravarty for a talk.
So good morning, everybody. Thank you, Dr. Dhawan, for this nice and very kind introduction. Oh, okay. Is this good enough? Yeah. Oh, this will come out. Yeah. Yeah. So, okay. So I first wanted to say thank you to all of you who have come to this presentation, and also to, in particular Dr. Dhawan for inviting me for this. I mean, it's really an honor. So today we are going to talk about hybrid digital twin. I am not, I don't know the familiarity of this audience with this particular with this particular topic or associated topics. So, however, I hope you will find this selection interesting, and hopefully for those students who are here, you'll go back with some ideas that you would like to continue to pursue further. So, with that, let me go into the how I've organized the talk. I'm going to start with a little bit of an introduction about myself and the company that I work for. Then I'm going to talk a little bit about the topic, which is the hybrid digital twin. I'll try to introduce it. And then go a little bit deeper into basically the two main application areas, which is fluid system and rigid body systems. And of course, these days, no talk is going to be complete without a discussion on how generative AI is making or disrupting any and every field in engineering. So I will touch on that. And then, of course, hopefully we'll have time for some conclusions. So I'm hoping this will work the way it's intended. Okay. So I think this probably can be skipped, but I just wanted to one more time reiterate that I've been really fortunate to be part of three iconic institutions. I, of course, did my undergraduate from IIT and then followed up with my MS and PhD at Yale. And then I have spent my entirety of my working career at Siemens Technology in a variety of roles. As Dr. Dhawan said, I managed a research group for many years. Currently, I'm focusing more on technology development, which is this hybrid digital twin, which sits at the interface between AI, simulation, and control. So now moving on. To introduce my company, Siemens, I thought it would be best to start with a quote from our global CEO. Siemens is very active in multiple sectors, which is what we call industrial sector, infrastructure, mobility, and healthcare. Industry would be factories, power plants, and so on. Infrastructure would be, for example, this building, smart buildings, electric grids. Mobility is, of course, anything that helps you move from one location to another. It could be traffic systems. It could be trains. Siemens actually makes trains. And, of course, healthcare. So many of you may not know about Siemens, primarily because Siemens actually operates more in the industrial space and not in the consumer. It really doesn't have a product that faces the consumer. It actually supports automation and digitization for the industrial space. So you may not be aware of it, but I think the next slide, next slide would, if you just look at this particular collage, you will clearly see why how Siemens is intertwined in your daily life. For example, if you are coming to work in a car, it is very likely that this particular car was designed using Siemens software. If you were to be basically taking a train, it's also likely that the train has been built by Siemens. For example, Amtrak and New York Transit is basically a major customer for Siemens. Then if you were to say, we are all of course, the electricity comes from the power grid. While Siemens does not maintain the power grid, it actually creates the transformers and the controllers that go into the power grid. So that is one thing. And now, of course, every day, these days, everybody is using electric cars. So those chargers that you see out there, many of them are made by Siemens. So, and continuing on, as I said, I already touched on the building side. In fact, if you were to go to your basement and look at the breaker switches, most likely they are made by Siemens. And then if you were to, God forbid, if you have to go to a hospital and there is a need for imaging, most likely those imaging machines are Siemens products. Of course, there are in each one of these, of course, there are competitors. But the bottom line, what I wanted to say is that Siemens may not be visible to you on a regular day-to-day basis as Apple and Microsoft is, but Siemens has a lot to do with your daily life. Just as a side note, Siemens is roughly 50,000 employees in the US and 350,000 globally. So it's a very large, it has a very large portfolio, and it's a very large presence in the US itself. Personally, I am located in the Siemens technology or Siemens corporate technology. And we are organized into these kind of 11 verticals. I spent most of my career in actually data analytics and AI. And then at some point in the last 2-3 years, I have been focusing more on simulation and digital twin because, as I told you, my interest has shifted to the use of AI within this particular, on digital twin simulation and so on. So I wanted to focus on that particular area. But however, as you can see, these are some of the, if you look at all of them, they will clearly see how the industrialization support of, how Siemens supporting industry is consistent with this particular set of verticals that we have. And how do we work? Siemens technology, I'm saying this for those who would want to consider a career at Siemens. The way we work is, we work in a very large ecosystem that includes the universities. We work with all universities, including NJIT, even though we have special relationship with those 4 universities that you see over there, Georgia Tech, CMU, Berkeley, UC Berkeley, and MIT. We also work with national labs. We work with federal agencies, different manufacturing institutes like ARM and MXD. And of course, our customers that are, that are spread throughout the country. So this is the ecosystem within which we work. Now, that's the introduction. So now what I'll try to do is to introduce the topic of hybrid digital twin. I'm hoping this click works. Yes. Okay. So first, let's try to define what digital twin is. Digital twin, as the name implies, is basically trying to create a digital replica of a physical system and trying to make sure that this particular replica, are you able to hear me properly? This particular replica remains updated over the lifetime of the system. And by the way, there is a National Academies, Dr. Dhawan was talking about it. There is an initiative within the National Academies led by Professor Karen Wilcox at UT Austin to actually come up with a more updated definition of digital twin. While that is still in the works, this definition that I have over there is the one that is currently the most accurate and up-to-date. While I'm not going to read the definition itself, I just wanted to emphasize on the fact that the value of the digital twin goes all the way from product conceptualization all the way to its lifetime manufacturing, operation, and then finally into, basically recycling or retirement of the particular product. And whether you are talking about let's say a aircraft or a railway bridge or for example, a cancer patient, managing a cancer patient, right? If you were to have a digital twin, then the value of the digital twin is in the ability to make better decisions while the system is in operations. So with that, let's see. So here is while the exact wording is yet to be, is going to come out, what is not, this particular architecture that I have taken from this National Academies, because I participated in some of their workshops, tells you what or how a digital twin is created. So obviously you have a physical system, and then you try to create a virtual representation from that by solving certain problems, for example, certain inverse problems, because you get some data and you try to find out what the model behind it. You, of course, data assimilation, sensor fusion, model adaptation. So those are all topics that you have to address to be able to come up with a good replica or a good replica of the physical system. Now, of course, that is only one side. That what's the value of this if you don't really are going to use it? So what are the uses for it? For example, basically control, planning, optimization, different types of decision making. And in between, you see that little circle that basically says that constantly this particular digital twin needs to be updated and maintained. And for that, validation, verification, and uncertainty quantification becomes very important. Any model that you create, whether you are using data-driven methods or physics, first principle-based methods, if you want to be able to use it on a regular basis, you must make sure that it is trustworthy. And trustworthy means that nothing is going to be accurate, but if it's not accurate, you have a good understanding of the uncertainty that is creeping into it from a variety of different sources. So that thing that in the center is also just as important as all the other problems that you see on the other side. So that is what the architecture is. Now, so the digital twin, of course, is a very happening field. And however, we are all aware of some of these. I think you have seen the slide. So you are all aware of the recent, let's say, onslaught of different new developments, both in terms of algorithms and computing hardware that is basically disrupting the entire technology space. And digital twin is no different. So it is also being constantly disrupted. And so what you see over here in particular, for example, some of you are probably familiar with it. I'm sure you are familiar with, and or you have seen in the news, for example, Metaverse. I mean, we have a company which named itself Metaverse, Meta. Then we have, of course, generative AI. We are in the big revolution that is there today. And of course, behind that, obviously, the hardware that has come from primarily NVIDIA, but of course, other companies as well. And then there are a bunch of technologies, especially when it comes to the hybrid digital twin or digital twin. These are the things like operator learning, differentiable physics, physics for neural nets. I'll touch on some of these topics, and so on. So you have seen all of this, and these technologies are actually disrupting the hybrid, the digital twin, leading to what I would like to call hybrid digital twin. So now, let's see what I mean by hybrid digital twin. Is basically a system that or a simulation or digital twin trying to get, bootstrapping digital twin technologies, which were primarily driven using first principle methods with AI. And then, of course, the reverse is also true, because once you have a model that has been created using, let's say, first principles, it is going to be able to generate data, and this data can be used to train it. And why do we need that? For example, if you are trying to control a system, there is no way that you can do the simulation from first principles. These are very computationally intensive tasks. So instead, if you can create a so-called surrogate model, which is a neural network, then you can simply evaluate that model, right? Once. So neural networks or machine learning has this beautiful benefit of trying to move the computational task from runtime to training, so which is offline. So that is the benefit. And once you do that, the hybrid digital twin, that's why I put over there, is the evolution of digital twin to the next level through the integration of simulation and AI. And that is what is enabling the metaverse, because we know a lot of things these days can be done in the metaverse. You can play games and all of those stuff. But if it was not for the digital twin or the new methods that are appearing because of the digital twin, that wouldn't be possible. Leading to improved speed and accuracy, increased productivity, better insights, and of course, better interactivity. In addition, I wanted to draw your attention to this particular paper in case you're interested. There is a very recent, this is a recent paper that came out last year that says the hybrid digital twin is basically driven by these 9 major technical motives. And of course, you can, many of you will find your familiar favorite, technologies that are out there, inside this list. Continuing on, I thought, that is you just saw that, I said that there is this bootstrapping or the closed loop interaction between digital or the physics-based simulation and AI leading to digital twin, hybrid digital twin. So I thought I'll just do a quick evaluation on, the similar thing that is happening with AI or traditional machine learning. So obviously the first phase of machine learning, machine learning has been, neural networks have been around for a very, very long time. But, the one, when it started really starting to make a big difference and slowly becoming ubiquitous, the first phase, 1990 to 2000, was basically trying to do back-end data modeling, leading to, for example, improved search, supply chain management, and so on. And that led to the emergence of companies such as Google and Yahoo, right? The next was trying to introduce some of the human concept, leading to recommendation systems, electronic commerce, and came the Netflixes and Amazons of the world. The big difference, big phase started in around 2010 or 2012. There's a very, I would say, groundbreaking paper by Hinton that led to the emergence of deep learning. And that has revolutionized computer vision, natural language processing as we know it today, speech processing, and many other technologies along with that. And finally, this currently everything is being, as I said, once again disrupted by the emergence of metaverse, generative AI, and so on. So foundation models. So these are, of course, every researcher will have their own view on this. This is just my view. Actually, I took this from, initially adapted from a presentation by Professor Michael Jordan at UC Berkeley. So now I'm going to talk a little bit about what hybrid digital twins mean and what the value of that is. So I really like to start with this particular diagram. If you look at it, all it is, it's a very simple modeling of planetary data. There is nothing more to it. On the left, you see we have introduced a little bit of physics, which says that the sun is at the center. And on the right, you see we don't have that knowledge. So we say that Earth is at the center. Now, what that little bit of physics, you can clearly see how much difference it makes in terms of our understanding from the data. So the same data, it's a very simple data, but this little bit of physics makes a huge difference in our understanding of it. By the way, what you see at the bottom is a very interesting chart that tells you it took more than 1,000 years to go from geocentrism to heliocentrism. And you can see, even though initially people like Archimedes had the right ideas, it was not until another 1,000 years that this particular thought was, or this particular notion was, formally established. So it's a very interesting, thing. So now, the other thing I wanted to bring your attention to is, you see this, this is the eagle in flight, right? This is a majestic view of, when we want to learn about, or when we want to model dynamical systems, we obviously want to learn from nature. Nature is full of dynamical systems. Whether you look at this eagle flying, or you want to look at the waves in an ocean, and or the streams going down, these are all dynamical systems. So now, so in this case, I wanted to show this because this is this kind of flights, how eagle does this, how eagle manages the turbulent environment at different time scales using acceleration is something that is really interesting. And by the way, this particular paper that I have listed there, that coming from the proceedings of the National Academy of Sciences, it also showed up a couple of years back. It's not a very mathematical paper, but it tells you how the eagle manages the turbulence. And by the way, this is something that we all, turbulence. So that is obviously a very interesting thought, and we, hold on to the idea about turbulence. We will come back to it in a moment. But first, I wanted to also say, what are the foundations of digital, hybrid digital twin, or for that matter, even digital twin? So basically, at the back end, we have some dynamical systems, and we are trying to learn the models of the dynamical system through the observations that we are making, right? So effectively, to do that, we have to solve an optimization problem. It could be either directly and using first principles, or we can try to solve in a data-driven way, which would be some form of machine learning technique. Now, just like, as I said, this heliocentrism versus geocentrism, sometimes inductive biases or the physics, little bit of knowledge about physics helps. For example, many dynamical systems out there, if you obey conservation laws, there are symmetries that to be taken care of. So much of the So if you try to take the physics along with the optimization, then you have a much faster and better way to learn about dynamical system, and hence come up with better design. For example, if you were to design a car, that is something that you need to do, or an aircraft, and so on. And then, of course, to predict and control. And in terms of the modeling, the simplifying transformations or hidden patterns must be, need to be discovered. And by the way, this theory has been there for many years. There is nothing new in this. In fact, one of the most important theoretical foundations of this particular knowledge about dynamical systems came from the equivalence between symmetry and conservation laws. So anytime you see some symmetry, often in a dynamical system, there is a conservation law behind it. Was first introduced by Emma Noether, and I would request you to, especially the students, check her out. She is one of the most underrated but most influential mathematicians out there. You can clearly see, 20th century, and even Einstein recognized her brilliance. But it took a while for people to recognize how the influence or the power of that, what she said. So now continuing on, so where do we find hybrid digital, in use cases? Obviously, I'm from the industry, so I would like to work on topics that are relevant for the industry. So hybrid digital twins, you don't have to look very hard to find problems which, where the hybrid digital twin is relevant. For example, it is there in turbomachinery problems like rotating equipments, like gas turbines, the car, the motors, and so on. And then, of course, for different multi-physics simulation for hydraulic metal forming machines, flow control in an aircraft or what have you, design of cars, grid control, which is what is needed to keep the electric grid on, and and then, of course, train control. So it's ubiquitous. There are many, many places for which we need to, or we want to create, understand the hybrid digital twin and try to use hybrid techniques to model it. So then, so first, the first couple of first, I would like to talk a little bit about how hybrid digital twins are used for fluid systems. Before we focus on that diagram or the simulation that is running out there, I wanted you to basically make you aware of turbulence system. Turbulence is something that any one of us who have taken a flight will probably experience, right? But you don't have to go to an airplane to experience that. In fact, if you were to, whenever you are stirring your cup, you are generating turbulence. Turbulence basically is created whenever there's an excess kinetic energy in any part of a fluid. You probably either introduce it by stirring it, or it comes from another object or what have you. In fact, that is the reason why if you were to stir your cup of tea or coffee, you will see the turbulence that is generating slowly inside that. But if you were to try to do the same thing in a pot of honey, you may not be able to do that because the viscous forces are high enough so that it is not allowing you to generate that much turbulence. So you need a lot more kinetic energy to do that. So now what you see over here, now let's come back what you see over here. This is basically direct numerical simulation of a turbulent boundary value problem. Now, as I said, turbulence, starting with turbulence is very important for a variety of engineering problems such as aircraft control, even, for example, trying to model the blood flow in a heart so that we can come up with better intervention and diagnostics. It is also important for understanding ocean currents so that you are able to design better ships. So there are plenty, and likewise for designing better aerodynamics for cars and so on, right? So there is a lot of applications where this is important. Normally this is achieved using simulation. However, to do a simulation like this is very expensive. So one of the biggest problems that people want to get at or introduce AI or hybrid digital twins is to try to find alternative ways to or reduce the amount of computation that is needed to model this fluid. Now, if you try to look at this particular simulation, what you will see is that as the Reynolds number go up, and by the way, Reynolds number is basically higher Reynolds number means means low viscosity. So lower Reynolds number means higher viscosity. For example, honey will have a much higher viscosity and hence much lower Reynolds number than water, for instance, right? So as you see, as the Reynolds number go up, you can clearly see that there are these large structures that are emerging. So, and these large structures are the ones that carry most of the energy and is responsible for much of the turbulence, and hence we want to approximate that, but we don't want to worry too much about the smaller, less energy carrying structures. Now, this can be attained using machine learning. And in fact, what I wanted to show you here, now I promise you there won't be too many equations for this, but I still wanted to bring this because what you saw in the previous slide is basically solution of just the first set of differential equations, or it's actually PDEs, set of PDEs, that there is just, these are what is called Navier-Stokes equation, and there is a momentum and the mass. Now to approximate that or come up with, as I said, simpler method to solve it, people look at what is called Reynolds decomposition. And that is the way they do it is the simplest way by which many of us who have ever used signal processing do it, which is to say that the instantaneous, in this case velocity is what they're trying to learn, is a sum of a mean value plus some fluctuations around it, right? So that is what you see over there in the Reynolds decomposition U. And then, of course, you take this, the approximation, substitute it in the first two equations, and you get the others. What is more important, not necessarily to look at the equations itself, but what I wanted to say is that there is this type of, to come up with this approximation and to solve it, people used a lot of engineering, basically first principles approach by doing experiments, trying to come up with these some approximations. So as early as 2016, people started realizing machine learning can make a big difference. And in my mind, the first real valuable hybrid digital twin techniques came along, trying to do what they call it Reynolds decomposition or Reynolds average numerical simulations, right? RANS. One other very interesting problem that very interesting development in hybrid digital twins that I wanted to bring your attention to is so-called physics-informed neural nets. This was pioneered by Professor Kaniadakis at Brown. And it's a concept-wise, it's very, very simple. All it does, again, I'm rewriting, this is what you see at the top is a rewrite of the same Navier-Stokes equation that you saw in the previous slide. And basically, we first convert those equations into a constrained optimization problem, because many of you have solved least squares problems, so you know that you can take an equation and convert it to an optimization problem. So this is how least squares problems are. Least squares are often used to solve a system of equations. And then you basically try to use the trick of Lagrange multipliers to convert that to a multi-objective optimization. This is also, I'm assuming most of you in engineering have tried or have done. Now, the only difference that he did, which is where the real innovation comes in, is instead of using first principles method to solve an optimization problem, he used a neural network to do it. Now, I'm not going to tell you exactly, it is an interesting technique. It is still being developed. Let me see if this particular, what you see on the right is basically the heat diffusion equation. It's a pin-fin problem, and it's inside the core is being heated, and there is the heat is radiated out. I don't know if they can run this simulation. I think this is a video, if you can click on that. Let me see. Okay. So what you see is the core is heated up first, and the heat radiates outside. So there is nothing big, but nothing. This is just a solution of the heat diffusion equation done using the physics-informed neural network. So just this is previously this used to be solved using finite difference or finite element method. Now this is also an alternative way to do it. And by the way, there are many problems. And here is one that we looked at personally, where we wanted to, these days many of you are driving electric cars or are aware of people driving electric cars. And I think you know that electric cars have this challenge that during extreme conditions, the driving range reduces because the battery is used for other purposes. For example, maintaining the comfort level within the cabin, right? So now, to understand the comfort level within the cabin or finding out the heat distribution within the cabin, the approach would be to do a simulation, right? But that, of course, is very expensive. So one way to do that, one way to go around it is to use, as I said, physics-informed neural networks to model this as using a machine learning or a neural network. That way, you can control use the HVAC. You can control the HVAC so that you maintain some comfort. However, you try to maximize the driving range. In fact, a recent study looked at the fact that if you were to operate a few degrees higher, there is significant reduction in the in the driving range. Another problem that we looked at, again, the same Navier-Stokes, but let's see if we can see this. Yeah. What you see over here is on the left. So obviously, as I said, simulation is expensive, right? However, if you were to do a simulation on a low resolution, that is going to be less expensive, right? So what I tried over here is to see if I can seed a problem with low resolution simulation and then use machine learning to upsample it. Then you get the benefit of a full-fledged simulation with very much lower cost, right? So this is some work that I did with a student of mine, and Others have similar work out there that you can look at. I think you already saw the simulation. So that is one on your left again is the low resolution. On the middle is the high resolution, actual high resolution. And on the right you see the model predictions. How are you doing on time? Okay, so there are a few other things I wanted to touch on. For example, also on rigid body, there is a similar activity that that you can do for rigid body systems, and you can see over here your regular pendulum, and this is, by the way, a double pendulum. And basically, what I wanted to make the point here is that you can solve for pendulums very easily, but when it comes to double pendulums, you cannot solve it directly without introducing some amount of physics, hence the value of, again, hybrid digital twins. That physics happens to be called, happens to be that the total energy in a system is preserved, and this type of systems are called Hamiltonian systems. As an aside, there is an interesting, in case you want to read it up, there is something called interplanetary network. Basically how you can move from distant, how you can place an object in a distant planet by using very low energy, and that is also related to this. So I'm going to skip this slide and directly come over here to say that if you again introduce this little physics of the fact that the total energy is conserved, you can see on the left the prediction problem of basically predicting the position of this pendulum is done much better when you take this so-called physics into account. And likewise, on the bottom, you see the control problem, the corresponding control problem, where you try to control the pendulum or the cart pole or acrobat. So this little bit of physics makes a huge difference. And by the way, this is also a paper that we published at ICLO. Moving on. As I said, there are problems. There are a lot of problems, similar problems in other areas also. So I will skip this one. Now, generative AI, I think we are all aware of, has also made a difference. So I'll quickly go over it. On your left, you see the familiar double pendulum. And by the way, you can use generative AI. This is just using a prompt to solve it. And on your right, there is another benchmark fluid dynamics problem called the lid cavity problem that can also be solved using generative AI. So generative AI is making a big difference, and it is, again, also adding to, or accelerating the emergence of hybrid digital twin. And then, of course, one can get more aggressive or more, more ambitious. Now, the work that Siemens is doing in this space, I am unfortunately not going to be able to go deep into because of proprietary reasons, because this is ongoing work. But one thing I wanted to draw your attention to is this work done at MIT, where they try to go from a sketch to a prototype using 4 different steps of going from sketch to text, text to images, and so on. And I think that is where those are the topics that I had. And so what we covered today is basically trying to define hybrid digital twin and give you some examples of how hybrid digital twin is making a difference in this, making a difference by bootstrapping AI and simulation. And several technologies are basically participating in making that happen. And I introduced you, for example, this neural operators, physics-informed neural networks, how we can manage turbulence, and also the little bit about generative AI. With that, I would like to thank you for your time, and thank you again, Dhawan, for the invitation.
Thank you so much. Excellent talk. And the thing that I was very impressed that you were able to connect the fundamental of physics and the mathematics to the computer simulations, to the applications, showing that the knowledge from the basic sciences that our students are gathering, because many times they think, why you are taking 3 courses in mathematics, Lagrange variables, optimization and everything, but you showed them that there is a connection of using the physics of the whatever the system it is, based on the fundamental understanding of mass, conservation of energy, to use those as a boundary conditions for the simulation to create a digital twin. So before I say a couple of questions of my own for curiosity, I wanted to open it for our students, because basically what I mentioned to them yesterday, that they will have an opportunity to ask question to you, and I wanted to request them break your barriers of communication and hesitation, and ask. This is your opportunity. So from the media services, could we have somebody move the mic around? Yeah. Okay. So raise your hand, and my friend is going to reach to you. Yeah.
All right.
Stand up, please, and tell your name, and then ask the question.
So, hello, my name is Ranu. I was one of the presenters today. Question is, so I was able to understand a lot of during the AI modeling, because for what I'm doing or what some of my peers are doing, as far as trying to use machine learning to recreate some of the data that we lost, during a geomagnetic storm from the sun, or as far as trying to recreate old data using machine learning. So I understand that aspect of it, but for things that are more complicated and that we don't know the models for, we don't know the physics for, trying to use machine learning or AI to test the emotions, or for counseling. So what types of things do you have to think about when trying to create a model for those type of things?
So, okay, I think that's an interesting question. Now, if you think about this, where is the value that is, where does it make most bang for, or return on investment, right? Anything that you try to do is cost, in some sense, cost is effort or money, right? The value comes when you have incomplete information from both from the data side and maybe even from the physics side. Because if you have complete knowledge of physics, then you can do first principle simulation, unless of course there are cases, of course, which is where I introduced this problem of RANs, and how you can use, how you can approximate the lower, the lower energy or the smaller structures, the energy transport that is happening in the smaller structures using the larger ones, right? So, for example, if I were to model, let's say, the temperature distribution in a gas turbine, right, or any complex system, right? Now, you may not have all the observations because simply because there are many places where you may not be able to even place sensors, right? So you have incomplete data, but you have some knowledge about how combustion happens, for instance. Or in this case, as I said, you may have some data, but you also might have some knowledge about the fact that the total energy is conserved. So then once you introduce that, this is where the value is. And by the way, I showed you this control, of course, on toy problems, but this is, using this so-called Hamiltonian control is a big thing in case you have, I'm sure if you were to take more courses in controls theory, you will see that Hamiltonian systems are a very important part of it, or its corresponding Lagrangian system. So yeah, there are many problems where you don't have enough information, or in which case AI methods will not will be biased where you have information, and will not be able to address those areas where you don't have enough. And in that case, for example, introducing this kind of physics makes a big difference, or speeding up the solution itself. There are many, many applications like that.
Just the comment, or what I used to do was multi-grid optimization. And the point that you made over there, that you go with the lower resolution. So when you have a dispersed incomplete search space. You start with, you don't know where the solution is. So random walk method or any particular type of the technique is going to be very, very computationally expensive. So I think one of the things that you showed over there that you could do the simulation at a lower resolution, learn by doing that particular simulation, and that will improve your understanding of the behavior of the dynamic system that you could now go at the higher space.
Exactly.
Right?
Exactly.
So-
Because there is never enough, let's say, compute power or time to do all the simulations to, generally what you're talking about, you're trying to basically move to, sample a large space, right? Now, there is never enough time to do a proper sampling. Question is, where do you do the sampling in that case, right? So then this kind of approach.
So my connected question is, does like the multi-grid optimization where you have inter-level and intra-level optimization, does digital twin allow you to do in a more cost-effective way?
Depending upon the problem, people would use lower resolution problems, right? There is also the multi-physics sometimes. You don't necessarily try to take into account all the different physics that are relevant for this particular system, and then you basically. So there is a way to let's say divide and conquer, and then the benefit is the more inductive bias you bring into it, the better you can by using less data or using less computation. I mean, that is the bottom line. There is no free lunch. Either you have some knowledge or you get lots and lots of data.
Hi, my name is Yash Jain. I'm a math major, and I would like to ask if what the best resources are to learn physics-based neural networks. Also, one more question: could this digital twins be used to model sort of lake dynamics? Because I think lake dynamics are important to what I'm researching. So, if you could model the fluids in lakes.
Yes, absolutely. Both the answers to that is yes. In case you are interested, I would request you to look at. You go to the, as I said, in one of the presentations, in one of the papers, I think when I introduced physics into neural networks, I created Professor George Kaniarakis. So I suggest that you go to George Kaniarakis' website and in Brown and look at those. He has a sequence of papers in this space. There are other professors also. Caltech is doing some great work in this space as well. So especially when it comes to the atmosphere, so that is another place. You're basically looking at wake and things like that, right? So it's basically trying to model climate. There is a Professor Anima Anantkumar is doing a lot of work in trying to model the climate. So I suggest that you start with Professor Kaniarakis because he is doing, that would be a great resource for you. That's what you're looking for, right?
We'll take one more question. Yeah, okay, there are two. Okay, we'll take two. My question you already addressed, incomplete data observation and the lack of the knowledge in the physics model.
Hi, my name's Kabir Singh. I'm a mathematical biology major, and my research is in drug design. I was interested, and I wanted to hear you speak a little bit more about the use of the early stage generative AI in your use of the product design. I saw the little sketch, and then you created a thing from it, and I was wondering, were there any fundamental problems associated with it, like physics or engineering related?
For drug design?
No, for anything. I work specifically in drug design, but if you have something related to that,
I have not worked in it, but there are some, honestly, this is a very emerging field, and I am not going to be able to tell you on the top of all the activities that are going on, it's really difficult to even keep track of, even as a researcher. So I think when it comes to generative AI, people are trying to create foundation models, for example, to go from one scale to another. For example, going from the molecular level, like there are generative AI, but it may not be what you always, whenever we think generative AI, we are thinking about large language models. It doesn't have to be large language models, all right? So people are looking at that work of trying to see how they can straddle between different scales. For example, from the atomic or molecular scale to, let's say, particles and so on, right? So that is one that I'm aware of people are looking at, but there are probably many others. And this is something that is, also the AlphaFold work is an interesting example that you can draw from. But there are many other, there are many researchers out there, especially generative AI has a aspect for material science, for drug design. I think drug design is basically, if you are addressing at the molecular level, you can start looking at that aspect as well already. So I'm sure people are looking at it. I'm just not up to date with that literature.
Yeah, we use AI in our designing, but the problem is like what we do is we design the majority of it, and then we let AI do the rest. Sort of test it through like thousands of different configurations and stuff.
Right.
We let them do the heavy lifting. But my question was sort of.
You're looking at the fundamental side of it, right? Yeah.
I wanted to know if there are any fundamental problems.
So there is a lot of work at least in material science that I'm aware of, where you try to say that I want to have a material with this particular property. You solve the inverse problem, try to come up with what is that material, in terms of its composition. Mm-hmm. There are works like that, and you can imagine it fits an AI framework. It's the inverse problem that you have to solve, but it's there.
Okay.
People are looking at it. People have looked at it, actually.
Okay.
So.
All right, thank you.
Thank you. Last question, just out of time.
Hello, my name is Olina Sen. I'm a junior biomedical engineering student, and my research was on the natural frequencies of pupillary responses. And something that I've been seeing when doing my coursework and some of my research is that in terms of physiological systems, when you're looking at the behavior of them, you're also noticing the behavior of other physiological systems within that, because our body is it's a complex machine, every part working together. And because of that, when looking at patient data, each patient can differ based on, let's say, if they had a regular night's worth of sleep or if they had a past injury. And I was wondering, because you mentioned bias earlier, when training AI, I guess, with a lot of this differing data, how are you able to detect bias within the end simulations created, and how do you address that? This does not have to be from a healthcare perspective. I was just wondering overall in your experience. Thank you.
By the way, for healthcare, there is a lot of work that is going on, how to use, for example, healthcare data to create quote-unquote human digital twins, right, biological digital twins. There's a huge work, including in Siemens. I did not touch on that, but there is a lot of work going on in that. For this exact, there's a whole field of personalized healthcare or personalized medicine that goes into that. Now, for I think your larger question was, how are we going to know there is bias in the data, right? It is a loaded question because every problem faces this, right? So one of the things people look at is, very simple way if you can think about is to look at the distribution of the data, directly in that space. If it is not, then in some latent space that where you want to do the mapping. So that is. People look at that, and that leads to all kinds of uncertainty quantification techniques, right? So, so there is a lot of literature on that topic itself. Now, it is And there are ways to correct, for example, to reduce bias in systems, and people have always looked at it, not just because of the answer, because of generative AI or anything in recent. They have always looked at it because, and this is where the value of the large foundation models are, right? Because they look at so much data and so many parameters. It's unlikely to be, at least they presume there is not enough bias, not much bias. But the reality is there is bias. For example, large language models are biased towards English. And a few other languages where there is a lot of data available, if you were to use it for, let's say, I don't know, my mother tongue is Bengali, I'm sure it is not going to be as, it may not be able to model it as well. So there are, this translation will have between, using large language models to translate from one language to another works best when both the languages are popular. If it is less popular or less data has been introduced, then you will face the bias problem.
All right, thank you very much. Please join me in thanking Dr. Chakravarthy for an excellent talk. I hope that it added something very, very not only informative but inspiring to you, that you could connect what you learn from theory in the classroom to what you are going to be applying in understanding the problem and finding an innovative solution and then translating it to the applications for any impact that it would make for use-inspired application. That's all the ball game is about, right? So I just wanted to announce one other thing, that this topic is so much going to impact the current and the future research and development at the system level, that I have been designing a full-day CTR workshop, Center for Translation workshop, on October 22nd. So if you want to mark your calendar on generative AI from conceptualization to manufacturing. And Dr. Regina Mallard, who is the Chief Technology Officer for Digital Twin and AI, works at Siemens. She is going to be the keynote speaker. We will have the panel discussion and all other things. So you will see the announcement to the NJIT community. If you are interested in learning more about the applications, industry applications, and also the system-based solutions using generative AI and digital twin, join us on that day. So with that, thank you so much again. And I'm going to be quickly doing a couple of minutes. We are 5 minutes over already. Can you put my presentation? This is Dr. Chakravarthy, don't go away. Yes, so we have, can you put my presentation? So as a part of the National Academy of Inventor chapters at NJIT, we induct, every year we induct the new members to the NJIT chapter who has made contributions to the inventions and received the patents. These are the people who are visionary, who are inventors, who are innovators, and they found some innovative solution turned into the intellectual property towards their pathways for the translation to market. So this, these are our current NAI fellows at NJIT, and we are very, very proud to induct the 5 members to the NAI chapters at NJIT. You already listened to Dr. Chakravarthy, his patents and his leadership, and he has also received 2 times the Edison Patent Award. So it is our pleasure, honor, and to offer Dr. Chakrabarti, member of the NAI chapter at NJIT, as he is also supervising two UTRI students who presented here yesterday. The UTRI is Undergraduate Translational Research Internship. So he was very kind that we communicated, and he has supervised two students during this particular summer as a part of the Center for Translational Research and NSF funding of Accelerating Research Art program to NJIT. Have four faculty members who are displayed over here, who received the patents and have been doing pioneering research with the inventions and the innovations, and we are very proud to have them inducted into the NAI chapter at NJIT. We have only Yi Chen with us, so I will request Yi Chen to come forward. There you are. And Dr. Chakrabarti to join me on the stage. Could you give me this whole thing? Oh, sure. Okay. So I serve, as Dr. Lim said in the morning, I serve on the board of directors at the National Academy of Inventors. So I have the authority to do the oath ceremony and have the induction to the National Academy of Inventors as the member. So I'm very proud and honored to present the memberships to Dr. Chakrabarti and Dr. Yi Chen. So stay here because I need to do this formal induction. In recognition of your support and commitment to advancing technology development and innovation, I hereby declare and certify that you are members of the National Academy of Inventors and are granted all rights and privileges to the Academy. Congratulations. And this is the pin that you could use it.
Thank you very much.
So thank you very much again.
Thank you.
Thank you, Dr. Dhawan.
All right. Thank you so much. That concludes the NAI chapter induction ceremony for today. And I would invite you to join us for lunch, and we will be back at 1 o'clock to resume the session. Thank you so much.